So thank you, please. And I thank the organizers, the Kutuhali and Kala Suruchi, for giving me this chance. It is very important to discuss science with a citizen, because we believe that science is a citizen's activity. Science is supported by the taxpayer, and that should never be forgotten. And as a duty towards that, it is the duty of a scientist to interact with the citizens. Nowadays, this has been recognized by institutions of science also, and as a result, most institutes are now mandated to open what is called their public outreach program. In fact, in my own institute where I worked, I was the person who started it. And at the time of the International Year of Astronomy, that was 2009, the 2009 was in commemoration of 400 years after Galileo used the telescope to look at the stars. So it was at that time that I coined a slogan, and that slogan still continues to be used, and that is universalize the universe. Universe cannot be purchased. You can purchase land, forest land, anything, but the universe belongs to everyone. It cannot be purchased. And that is also a spirit of science communication. One of the other things that I would like to tell, the science communication actually has to be done by the local language. And one of the pioneers in that, at least in India, was Professor S.N. Bose. Unfortunately, my Kannada is not up to that. Okay? And let me tell you a story. And story was when Lord Rutherford had found his alpha scattering experiments and discovered the nucleus. He was invited to go to Sorbonne University in Paris and give a lecture. Now he didn't know French, or maybe his French was not up to the mark. So he deputed somebody called R.H. Fowler to give the talk. So R.H. Fowler, with his own French, I don't know how good his French was, he gave his lecture in French, and after the lecture was over, the chair said, now it is open for discussion. There was no question. Ultimately, somebody from the back raised his hand and said, Monsieur Professor, will you now translate your lecture into French? So those risks I don't want to run into. So I'll speak in English, and I believe that this kind of interaction, we also have our ideas, but they did not succeed. That for the Northern India, from AI Pearson, we suggest that there should be something called Science Guftagu or Vigyan Ki Kahaniyan. Okay. Some decided there should be Science Adda. Adda is a very famous word in Bengali. It's an institution. Adda is aimless chatting. Okay. So anyway, please. Today, the title, as I've said, is What Are Black Holes? Yes, this is, okay, then, right. So, the title is What Are Black Holes? There's a question mark. Okay, it could be an examination question, or where you have to answer a question, or if I remove the question mark, it can be what are black holes, isn't it? That you narrate what are black holes. Now I think the way I will speak it will be partially satisfying both. Because in science, questions come and then progresses. Yes? It is never that you find a solution and then look for a question. It is always a question comes and then you look for it. So, let me see. Let me first begin. It is not only, it is a story of a history that I would say, that where we have reached about our understanding of black holes. Now, early ideas came from these two gentlemen. John Michell in England, 1784. So you see the ideas are quite old. Yes, about 230 years old. And the famous mathematician Pierre-Simon de Laplace in 1796. Laplace is a famous mathematician and his book on celestial mechanics is famous. And what were their ideas? The ideas were very elementary for that time. So though they were giving this hypothesis, I would like to tell even 100 years ago, people were not even sure whether there really are things like black holes. People even dismiss the ideas that black holes can exist. But as you know, that in science always it is, you have no space to sit or the real observational evidence came only 3 or 4 years ago. All right, and that is the journey that we will go through. Okay, that is the journey. Now let us look at the early ideas of Michel and Laplace. So here are they. On the right hand side, that is the gentleman's picture here is Michel, and the other one is Laplace. See, Laplace was commissioned by Napoleon to use his celestial mechanics to make calendars. Okay, so that if the royalty needed many things, that history I will not go into. I need it, if necessary. If necessary, I will need it. So royalty. So anyway, I will go to if you look at the picture, one thing we knew that there is something called gravity, but it is a constant gravity beating off. Okay, that always it is G on small g, I am talking of, that on the earth, small g is roughly 981 centimeters per second square. That is something. So that what happens, if you throw something up, it has to come down. Correct? So that whatever is the kinetic energy is used up in climbing the potential energy against the force. Potential energy is always positive if you move against the force, and negative if you move opposite. Yes, against the force. Force is downward, you're moving against, it's positive. And when you're moving in the direction, it is always negative. Now where the potential and the two has to be kept a constant. Kinetic, and that is called the conservation of energy. So they always knew that if you throw something, it will come down. The question still was not very clear whether light will, if it goes up, it will come down. Because the ideas of what we call a light quantum, etc., were not there. Except that Isaac Newton had said these are all particles. Now, why a particle of that kind would be acted upon by the gravity, it was not known. Okay, but they were conjecture that if it is so, the escape velocity for such a particle, here you can, this very small algorithm, that this is V escape, is 2gm capital N by c square, where m is the mass of the object. Okay. it cannot escape. And they knew perhaps that light has a very high velocity, though it was still not measured accurately. It is only a conjecture. Galileo had given certain ideas, and Christian Huygens had given certain idea that these velocities are very high. So, this is what happens. Suppose you have got a spherical mass m. Can I have the whiteboard here?
Yeah, definitely.
It is better.
Yeah.
So can you see from distance? So here let us have a spherical object. And what Newton had shown by his gravitation, that this force is inverse square. And gravitation is always attractive. There is never a repulsive force in gravity. In electromagnetism we have, but there's nothing. Everything has to be pulled. Okay, so if you are at a distance r from it, then gravitational potential is equal to minus capital G, then mass, that divided by r. So this is what. So that is what I have written. Potential energy is minus G, and if the object has a mass m, then it has to be, this is its potential energy. Now suppose I place myself on the surface of that spherical object, then at that point, mvr, which is its potential energy, will be equal to minus G, capital M, small m by r. Fine. But now let us allow the particle to move with a velocity of this one. Then it gets a kinetic energy, which I have written here, half mv square. This I think all of you know, isn't it? It is kinetic energy is velocity to the power 2 multiplied by mass and half. So what is the total energy? You add this, you find first term is positive, kinetic energy is always positive, and second term is negative. Okay? But now, if the second term is too high, then the total energy becomes negative. Okay? Which means it is trapped. Right? If energy negative means it is trapped, it cannot go anywhere. And that is where is the concept of an escape velocity. That v square, if it be less than twice g capital M by r, the particle cannot escape. So in this case, if it be at a distance r, the escape velocity should be equal to twice g m by r. Fine. This is for anything. Now let us see. This is exactly what I said now. That escape velocity is square root of 2gm by r. Now suppose I have got an object which is moving with the speed of light. Again, a hypothetical case, because we still don't know whether a photon is affected by gravity. This was never conceived of by Newton, but hypothetically we say that. Correct? So hypothetically say that such a thing is possible, and what should be the escape velocity? So what should be the mass and radius of the system, okay, of the spherical object, so that anything with the speed of light also cannot escape? So just instead of v escape, you put v, you put c. So you will find that in such a case, m divided by r, that is mass of the object divided by the radius of the object, okay. If it be greater than this, m by, just what is something? There's something wrong there. What we have said, that v square has to be equal to twice gm by r. And suppose this is equal to c square, this is equal to twice gm by r. That automatically means m by r should be greater than twice c square by g. Okay. So this is therefore m. Now this is what is very important. Let me tell you. That very often people say that it has to be very massive, but it is not merely very massive. It should be massive and very small. Like our galaxy has a mass of 10 to the power 11 solar masses, but still it is not enough because it is a highly diffuse structure. It should not only be massive, but it should be small. Unless the two are satisfied simultaneously, a black hole or so-called black hole cannot be formed. And this is the black hole condition. So what should be the value of R? R is equal to m. This is like this. R is equal to
mg by
mg
2gm by c square. 2gm. Yes. 2gm by c square.
2 should come in the
Numerator. 2gm by c square.
gm by c square.
And project rate is correct.
Yeah, and this we called what is called a Schwarzschild radius. Why? That I will come later because this was given by Schwarzschild. So this is the condition that if your object is such that this is greater than this, it can form a black hole, but of course it is from a hypothetical point of view, and there are certain universal constants here. One is small g, a capital G, which is the universal gravitational constant, and its value is given here. This is a constant introduced by Newton. And second is velocity of light in vacuum, 3 into 10 to the power 10 centimeter per second or 300,000 kilometer per second. These are the universal constant. Now these were determined very accurately. By Cavendish determined the value of G, and that is the value that I have given before. It is a very small quantity, 10 minus 8 it should be there. Gravitational G is equal to 6.6732. Then to the minus 8 is missing. So that is very accurately found. And the speed of light was found. So this is the picture, a drawing of Cavendish. He was also the discoverer of hydrogen. Okay. And he determined very accurately the value of G. And because of this accurate determination, we know what is the mass of the sun. There's no other way. Okay. And measurement of C, the speed of light, were done by two people. One of them is Fizeau and another was Foucault. So here is the picture of Fizeau and Foucault. A classic experiment. It was done, I have no time, but it is one of the beautiful things. So their C value was also known. G was known, C was known. So that way you can find out what should be the condition M by R. What should be the condition to have a black hole? Okay. It turns out that both mass and radius are going to be very heavy and very small. So most people thought it is not possible to have. About 100 years ago, people thought that it is never possible. But then the question comes, all these predictions have come from Newtonian mechanics, considering that if the photon is attracted by gravity, but there is no evidence. Then how do we conclude? And that comes with Einstein and general theory of relativity. Now we do not have the time or the apparatus to get into this. One thing can be done, can be said, that if any event takes place, okay, and there's a time interval t for that. Then somebody, and if that event takes place in presence of this high mass, in presence of this quantity, then the time interval that we will see is going to be longer. T divided by small quantity, time interval becomes longer. Okay? And the length intervals become shorter and shorter. Correct? Now let us see the fun. Suppose I go at a distance r equal to rs, then you see in this case the denominator becomes 0. Okay? Anything that is divided by a small quantity means it is going to be long. So any time interval is going to be inordinately long. We will believe as if nothing is happening there. And any distance will become short. So what would that mean for light? For light it would mean that suppose this is a wave, electromagnetic wave, and suppose this is its wavelength, lambda. So it is a length, isn't it? But if you are at that Schwarzschild radius, then that length squeezes itself to 0. Correct? We don't see a wave. There are another way of saying that suppose its time period is t. So time period that of the event actually happening is t, then we will observe it as t divided 1 minus rs by r. When r equal to rs,
0.
what happens? It goes to 0. Divided. So the time period is infinitely long. First of all, wavelength has been squeezed to 0 and time period has become very long. That means we do not see it even temporally changing. So this was the approach by which general theory relativity said that even light loses its existence. Okay? So space-time ideas completely collapse. Correct? So this is the way. So what happens at r equal to rs? As I said, length is squeezed to 0, time intervals becomes infinite, thus for light, wavelength becomes 0, frequency becomes time period, frequency becomes also 0. Okay, nothing is changing, everything is infinite time, so I don't see anything changing. So frequency has vanished, wavelength has vanished. And it's a terrible situation, isn't it? So this was what terrible situation people thought, that such things can never happen. Okay, including Einstein. How is it possible? Space vanishes, time vanishes. And Schwarzschild found all this, and mind you, the Schwarzschild value, what he found from general theory of relativity, is exactly what we had found. Okay, that means in our earlier case, a wrong approach gave a right answer. Correct? Because we were just... Okay. So popular ideas, what were the ideas in 1920s? That such things cannot happen. It's a catastrophe. Correct? It's a catastrophe. It cannot happen and it should not happen. And people said before anything squeezes to such a m by r value, some phenomena must arrest that collapse. Now what it arrests, no one knew, right? And no one ever knew that the stars can have such situations. But then the situation changed in 1930s. I would say from 1930s onwards. And this was, by that time, elemental composition of stars was found, that what stars are made of, by spectroscopy. They are obtained from spectroscopy studied of stars and the Saha ionization formula. Meghnad Saha was a pioneer in this. And what Saha showed is very important for future development. Because many astronomers thought that all stars are like our own, if the sun is like our Earth. Okay, it's only that it is hotter. But Shah ionization formula showed that most stars are predominantly made of hydrogen. Stars are hot and the pressures can also be calculated. And on the basis of that, stability of stars, etc., people try to find. For ordinary stars, Gm by R should be equal to kT by mass of the hydrogen atom. This is, I won't go into the detail, it is again a conservation principle. That is, if you are on the surface of a Earth, so this kBt by mh is the kinetic or half mv square for a hydrogen molecule at temperature T, and it should not escape away from this gravitational field, because only then that star can be stable. So this is all these people tried. That yes, most of the stars are satisfying this, but there were some, what I would say, black sheep, isn't it? But in this case, it was not a black, it was white, and that's the white dwarf star. White dwarf stars are found to be extremely hot. How do you find? From the spectroscopy studies. Oh, there's audience there also, I didn't know. So spectroscopy studies. Okay, and from spectroscopy colors you know how hot it is. Red stars are cooler, blue stars are hotter. And this is very close to white. That is, spectrum goes perhaps even beyond. So they must be very hot, and the white dwarf's estimate was 100,000 degrees Kelvin. Nothing much, plus add 273, it is comes to centigrade. But they are very faint. Hot but faint. How is it possible? It's only possible if their size is small. Very small size but emitting so much. Then how are they stable? If you put all this here, you said this cannot be stable. Correct? If you put on what I've wrote, this is for all ordinary, most ordinary stars, but for white dwarfs. So it means from an ordinary star it has collapsed at some stage. Where when it collapsed we didn't know at that time, because the nucleosynthesis was not known, but it has collapsed. And what should be the density? If you work out all those things, its density will be 10 to the power 6 grams per cc. Density of water is 1 gram per cc. Okay, that means 10 lakh times denser. Very solid. It is as if the sun is squeezed to the size of the earth. Sun is 10 to the power 33 grams, isn't it? As the whole sun has been squeezed to the size of the earth. How many hydrogen atoms per cc? 10 to the power 30 hydrogen atoms per cc. Okay, therefore how many electrons per cc? Hydrogen is only one atom, correct? So this is same. So then what is the distance between the electrons? It turns out 10 to the power minus 10 centimeters, very close to each other. And now comes a new physics, and that is called quantum mechanics. Till then, quantum mechanics was not known. If an object's confinement distance is small, is r, then its velocity has to be h is the Planck's constant divided by its me into r. Momentum should be h by r. Now mass of the electron, everything you know, it turns out that velocity of these electrons in that case, using quantum mechanics, would be at roughly 10 to the power 10 centimeters per second, and which is 1/3 of the speed of light. Correct? So electrons in white dwarf are not only moving under the Pauli principle, and all this was obtained by Pauli principle, and they are moving at very high velocity. So new physics had to come. So if you calculate, the kinetic energy for these electrons is 10 to the power minus 7 ergs. We have to use relativistic quantum mechanics. But at T is equal to 10,000 degrees, thermal energy per particle is much smaller, 10 to the power minus 11 ergs. So if I use that formula earlier, which I have written, that thermal energy is helping its stability, then we are actually ignoring bigger energies and dealing with smaller. So then Chandrasekhar did everything what is called the relativistic quantum mechanics, And he found the stability to be determined by relativistic quantum mechanics. And if there is a star of mass less than 1.54 solar masses, then it can stabilize into a white dwarf. But then the question comes, what if it is heavier? Then collapse will continue. Why it collapses? The reason is very simple. In gravity, there is no repulsive force. So here is the same body collapses under its own weight. Mass that is inside pulls the mass that is outside. And that can never be stopped. Unless there's something to arrest it, and these are the mechanisms. Then the question came, what if the mass is higher than this? There's nothing to stop its collapse. For heavier stars, electron degeneracy of Chandrasekhar cannot withhold the collapse. Then some other degeneracy comes that was determined in 1930s only after the discovery of the neutron. That neutron degeneracy, because it's again a fermion, it can stop, and one gets the neutron star, it can degenerate, and with a density of 10 to the power 12 grams per cc. Can you imagine 10 to the 12? That would be 10 to the power 12 to 10 to the power 16 times, trillion times. India is a what $1 trillion economy, all these we hear. Anyway, there are bigger numbers. So which is as good as sun being squeezed to only a size of 10 to 20 kilometers. Okay, so more compact objects are possible. Next comes, and this was the situation in the 1930s. Most believed that such collapses to neutron stars cannot occur. These were only hypotheses. Then there were theories by Volkov, Oppenheimer, Schneider, and Tolman. They considered dense star. They said we have ignored something. Chandrasekhar and others have ignored that space-time also gets curved, isn't it, inside? So let us include that. Of course, for a white dwarf, it is not necessary. For neutron star, marginally. But for if it be heavier, consider general theory for stability of massive and dense stars. At the surface, gravitational field very high. Space-time, therefore, there gets distorted. Pressure, temperature, etc. has to be recalculated on the basis of general theory of relativity. And they showed it will collapse further. Can anything arrest that collapse? Nobody knew. 1930s up to 60s work was only in the form of theories. Can GTR show that stars can collapse to something? Their Schwarzschild radius is this much. In the 1930s they say yes, but can it again collapse in a finite time? Because if gravity is so high, time intervals are, can it? They were not sure. But then in 1955 came another breakthrough in theory. It was from A.K. Raichaudhuri. And he answered, yes, this collapse can take place in finite times. And this was followed again in 1950s by Kumar and others. And from 1960s, it was further developed by Penrose and Hawking. And this is what comes in theory. Here I show you a picture of A.K. Raichaudhuri. He was my teacher in MSc. Okay, it was a pioneering work and it was a breakthrough. Okay. Now he was always clad in Bengali style, dhoti and kurta. Kurta like you, but dhoti. Yeah? Okay. But 1950s and 60s, something else happened. And these were observational. Radio astronomy developed. By 1950s, it has matured. Discovery of the pulsar in 1967, identified as the neutron stars, and discovery of quasar. I won't go into all these details, but these are very interesting phenomena, but without these, you cannot understand the journey. Right? In science, there are no super fast expresses. You have to stop at certain points and proceed. And discovery of the quasars. So, neutron star finally is identified. Okay, white dwarf is identified, dense matter, even denser matter gets identified. So the question comes, why not more dense? And hence, the point is towards a black hole. Discovery of quasar. Now these are all radio telescopes. The picture on the left here is an early radio telescope in 1930s, with the discoverer of radio astronomy, Jansky is, you can see him standing there. And these are now arrays of radio telescopes that are in operation. Even in India, biggest radio telescope is actually in India near Pune, GMRT. Okay, quasars, and here comes the question, what are they? Distant objects were emitting very high amounts of radiation, distributed all around us, all around the sky. But how do they get so much energy? This was the question. Answer came in 1969 by D. Lindenberg. He gave a suggestion that these are objects near a supermassive black hole. As matter falls into these black holes, they release their gravitational energy that is emitted as intense radiation. Okay, it was here, now it is falling in, falls here, releases kinetic energy, and the kinetic energy heats up other material, and these are emitting. And since it is falling with a very high velocity, huge amounts of kinetic energy are released, and so this is the source. So, quasars, where are they found? One idea was, and this I think is Lindenberg's idea, that our galaxy, our galaxy looks like this. It looks like a fried egg, isn't it? With a bulge, right? Then why is it so massive here? One suggestion was there is a very heavy supermassive black hole, and it has attracted all mass towards it. If it be very heavy, as you know, gravity is always attractive, it is going to attract mass. Okay. So this was a suggestion. Now Hubble has discovered many of them close to our galactic. Okay. Discovered what? Many quasars. Then the question is, if quasars are discovered, can we discover a supermassive black hole also? Now we are really looking for it, no longer theoretical issues. Okay. Any other evidence of supermassive black hole there? And it should be 2020 Nobel Prize in Physics, Reinhard Genzel and Andrea Ghez and Roger Penrose, they shared it. But before they could detect, an indirect evidence came in the LIGO, the collision between two 20 to 30 solar mass black holes. The idea is Einstein's fame rests on the fact that all his predictions are successfully verified experimentally in observations. Okay, very few scientists have ever had that kind of credit. And he was not a daydreaming scientist, he was very, very practical. Only one thing that he predicted was not verified in his lifetime, and that is the gravitational fluctuations travel as waves. And that was detected in, I think, 2016, and it was identified that these gravitational waves are coming because of collision between two black holes, quite massive, 20 to 30 solar masses. Because unless it is of this scale, we cannot detect, we cannot have any trace of a gravitational wave on Earth. Okay, since we found it, and unmistakably we found it, it can only come from collision between, it cannot come from rotating binaries or any such thing. Collision, such a strong effects, and these are coming from. So there's one indirect, but now we have to see it separately. And this is a exercise that Ghez and Reinhard, they were doing for the last 20 years. In fact, this lady, Ghez, I knew her once, about 30 years ago. She was still a PhD student. And Roger and Reinhard Genzel, she was still a PhD student. And she was trying to work out the sizes of binary stars. Stars one rotating around each other, just like planets do. And what she did, or their group did, not binaries anymore, but the sizes of orbits of stars near the galactic centers. Why? Because if there's such an intense gravitational field there, they should rotate very fast, okay, very fast, and orbits should be very small. Like our Mercury. It rotates very small orbit around the sun and rotates very fast, okay. So that knowledge they were using now here. And this is where they succeeded. And why? Why only those stars? Because then their orbit is 16 years. If you look at the sun's orbit in our own galaxy, it is 200 million years. So within one's own lifetime they want to check, within 16 to 20 years. So they did it. And the challenges were this, I think I got only 3 or 4 minutes, that they are very far away. 26,000 light years away, isn't it? Our galactic center. Time period of the orbit, yes, true, 10 to 20 years, so you keep on tracking them. Diameter of the orbit around Sagittarius A is D, is 60 light hours. See, this is light years. So this is small thing being viewed from a huge distance. You will see it as a point only, isn't it? So how to resolve this distance? So you can see, so D in terms of light years is 16 divided by 8,760 light year. Therefore, angle subtended. That this is D, and you're looking for a very far away distance. Correct? Angle subtended is, if you just divide this 4.39 into 10 to the minus 8 radians. It is just like measuring the size of 10-meter long objects placed on the moon, and where the distance is 3,84,000 kilometers away. It is just like that I'm sitting in Mysore and I've kept my book in Bangalore and trying to read from here. Okay? But that is the challenge that has to be met. And this was done. And it required tremendous technological advances. But mind you, another thing, these are not space telescopes. It was done through ground-based telescopes. So though space telescopes do certain things, but you can never substitute a ground-based telescope. You sit here and work. Anything comes wrong, you don't have to wait for the telescope to return from space. These are all done ground-based. And why I say this, ground-based has a disadvantage, and that is the twinkling of stars. So they removed all those errors and still succeeded in reading a book kept in Bangalore by sitting in Mysore. You know, this is the challenge. This is a different journey altogether. I won't go into this. And this, sorry, what happened? This is the end. Okay, sorry. I missed one slide or it got deleted. And that is a thank you slide. Okay? So thank you everyone. And it's, yeah. So I'll stop here. So this is a journey. Yes. And I tell you that this discovery wasn't possible unless we came to the 21st century. This is not the job of 19th century or 20th century physics or engineering. Engineer turned teacher, yeah? So there are moments of great glory for engineers also. Without engineering feats, these are not possible. Okay, thank you. I'll stop here.